Angle modulation is a type of amplitude modulation. It can be classified as phase modulation and frequency modulation. For phase modulation, it is generally use a smaller bandwidth than frequency modulation. In other words, more information can be sent in a given bandwidth in phase modulation. From the figure, we can see that in phase modulation, there is a frequency shift in the carrier wave frequency. The frequency shift depends on the amplitude of the modulating signal and the frequency signal. From the figure as well, the modulating wave, which is the wave in blue color on the right hand side, is modulating the carrier wave, which is the red color wave on the left hand side, and resulting the phase modulated signal, which is the green color wave at the bottom. Advantages of the phase modulation included that it produced a very stable frequency signal, and it is widely used for transmitting radio wave and is integral part of many digital transmission coding schemes that underline a wide range of technologies like Wi-Fi, GSM and satellite television. In the mathematical analysis of phase modulation, it is the process by which changing the phase of carrier signal in accordance with the instantaneous of message signal. The amplitude remains constant after the modulation process. These are the formulas for both the message signal and carrier signal, where Phi2 is equal to the phase angle of carrier signal. It is changed in accordance with the amplitude of the message signal. As an example, we can see from the formula shown here, after the phase modulation, the instantaneous voltage will be as both of these two formulas below here. Frequency modulation is defined as a sine wave carrier that can be modified for the purpose of transmitting information from one place to another by varying its frequency. In frequency modulation, the carrier amplitude remains constant and the carrier frequency is changed by the modulating signal. The principle of frequency modulation is as follows. First, as the amplitude of the information signal varies, the carrier frequency shifts proportionately. Second, as the modulating signal amplitude increases, the carrier frequency increases. And the last one, with no modulation, the carrier is at its normal center or resting frequency. The frequency wave R. Modulation index, MF, is the ratio of the frequency deviation, the delta F over FD, to the modulating frequency, FM. Frequency deviation, the delta F over FD, is the amount of change in carrier frequency produced by the modulating signal. The frequency deviation rate is how many times per second the carrier frequency deviates above or below its center frequency, and the frequency of the modulating signal determines the frequency deviation rate. The modulation of frequency modulation is as below.
There is a reminder here. Remember that the K1 is the deviation sensitivities HC over V.
Now grab this opportunity to test yourself. Bessel function is the equation that expresses the phase angle in terms of the sine wave modulating signal is solved with a complex mathematical process. The expression of a carrier that either being phase or frequency modulated by a single frequency modulating signal can be written in a general form as below there. From the equation 1, we have to remember that MF cos omega mt is the instantaneous phase deviation, which is the Bessel function identity states as the equation 2. If equation 2 is applied into equation 1, it can written as the equation 3 either. By expanding the equation 3, we can get the final equation as below. Jnm is the Bessel function of the first kind of n number of order with argument m. Each pair of sideband is preceded by j coefficients. The order of the coefficient is denoted by subscript m. The Bessel function can be written as the formula over here, where the n is the number of the side frequency or j and mf is the modulation index. This table shows the Bessel function of the first kind, Jnm, for some value of modulation index. This figure 2 shows the Fourier representation of frequency modulation. Here is an example question for the frequency modulation. You guys can have a try to do this. Now, we are discussing about the frequency modulation bandwidth. Theoretically, the generation and transmission of frequency modulation requires infinite bandwidth. Practically, frequency modulation systems have finite bandwidth and they perform well. Estimation of FM bandwidth can be made by two methods, which are Bessel function and the Carson's rule. For the Bessel function, if n is the number of sideband pairs, and line of frequency spectrum are spaced by Fm, thus the bandwidth B is equal to the 2 times n time Fm, where the number of significant sidebands n is more than or equal to 1 and the Fm is the modulating signal frequency. This is the equation to determine the minimum BW for angle modulation wave using Bessel table. Beside, for the second method, which is the Carson's rule. The Carson's rule is an approximation and gives transmission bandwidth slightly narrower than the bandwidth determined using the Bessel table. The Carson's rule shows that the B is equal to 2 times the bracket delta F plus Fm, where the delta F is the peak frequency deviation and the Fm is the modulating signal frequency. A low modulation index where the m is smaller than 1. The frequency spectrum resembles angle modulation double sidebands full carrier, and the minimum bandwidth is approximate by B equal to 2 times Fm. For high modulation index where the m is more than or equal to 1, the minimum bandwidth is given by B equal to the 2 times delta F. Let's do an example over here. As in frequency modulation, the total transmitted power is always constant and the total average power is equal to the unmodulated carrier power, that is the amplitude of the frequency modulation remains constant whether or not it is modulated. In effect, in frequency modulation, the total power that is originally in the carrier is redistributed between all components of the spectrum, in an amount determined by the modulation index, MF, and the corresponding Bessel functions. At certain value of modulation index, the carrier component goes to 0, where in this condition, the power is carried by the sidebands only. The average power in unmodulated carrier is defined as the PC equal to the VC square over 2R. The total instantaneous power in the angle modulated carrier, which is the PT, having the same formula with the average power. The function of the total modulated power will be as follows. Finally, let's test your understanding by doing this example now. That's all for the Chapter 3 Angle Modulation Part 1, and thank you for watching this video. See you. After all the lessons that we have learned, let's have a try to solve these exercises here. There is also provided the solution along with the exercise. Remember, practice makes perfect. Let's work on.